like to start with big data. Uh, so big data is basically a problem statement. So big data is basically a problem statement which the data analysts or data engineers have been facing with traditional RDBMS systems. While processing huge volume of data streaming in with high velocity, and different kinds of data, from different sources. It can be structured, unstructured, or semi-structured data. And it can be a combination of all these with audio and video data as well. So to address this problem, Google came up with the solution of distributed computing, where the data itself and the compute was distributed into different nodes. So with this solution and with some great contribution from Mr. Doug Cutting, we have this solution called Hadoop, which has basically two layers. One is compute and other is storage. So for the storage layer, we have this HDFS or Hadoop distributed file system, where the data gets stored in a distributed manner, and the input and output are also handled in this layer. And for the compute layer, we have different frameworks for different purposes. Like if you want to handle batch data, you have MapReduce. For stream data, we have Storm. And if you have a scenario like you need to handle both batch and stream data, we have Spark. And there is a lot more other frameworks in Hadoop. It's a small example I have given here. So let's move on and see how the Hadoop ecosystem looks like. So for importing the data into the Hadoop system, we have tools like Scoop and Flume. So this Scoop can import your batch data, and for Flume, it's like streaming data we can import into the HDFS. Zookeeper is the coordinator here. And the data, when comes in, it gets sliced into small pieces and distributed in the HDFS. And it is managed by the resource negotiator, here Yarn. And on top of it, we have the MapReduce, the compute engine, which is a Java-based compute engine. We have other various tools like high-level tools like Hive, Pig for data processing, Mahout we have for machine learning. Uzi is a workflow designer, and this we have another NoSQL database called HBase, which can be integrated into the system as well. So moving on, let's see how the HDFS data pipelines look like. So it basically follows a master-slave architecture, where we have the name nodes and some data nodes, which can be distributed into different racks. The name node basically plays the master here and keeps all the metadata. And the information about which block of data is residing in which node and how many replicas are there, if all the nodes are performing well, and all these kind of things. The data nodes here will keeping the data, will store the data and do the processing. Well, when a client submits a job to the name node, it will get back to the client with informations like where the data is residing and which nodes are supposed to perform this act. So with that information, the client will send the query to the specific nodes which are supposed to work on that requirement. And after the query's result has come out, it will be merged and sent back to the client. So we will see it in detail with the MapReduce workflow next. So in this slide, what we see in kind of yellow blocks are the blocks in the Hadoop distributed file system, and the white blocks are in the local file system here. So in MapReduce, we actually have two processes. One is a map, and the other one is the reduce. What happens is when the when the query is submitted, it will be split into the parts and sent to the nodes where it is supposed to perform, and the output will be stored in the output will be sent to the local file system, and then it will be sent sorted out and sent to the reduce phase where it will be merged and sent back as a result to the client. Another framework that I mentioned before was Apache Spark, and it comes with all these APIs and libraries. So this Spark SQL, we can do SQL queries, SQL kind of queries in Spark SQL. It's an API, an API with Spark Streaming for handling streaming data. MLlib here, a machine learning library which is available with Spark, and GraphS is also an API and library which we have with Spark to process graph data. So next, to compare with MapReduce, I'll show this data flow on Spark shortly. It also follows the master-slave architecture, where the master node communicates with the worker nodes via a cluster manager. The difference between Spark and MapReduce here, the data which the task is supposed to perform on which data is cached on the worker nodes. So the computation happens in memory, making it almost 100 times faster than MapReduce jobs. So with that, I'll stop with big data solutions and discuss something about the artificial intelligence, machine learning, and deep learning. So what artificial intelligence basically means is to giving certain kind of intelligence to machines to replicate human behavior. So what happens is it can to achieve this artificial intelligence, we have all these statistical, we have implement all the statistical solutions we have. Other than that, one of the solution with which we can achieve artificial intelligence is machine learning, which uses the neural networks for achieving artificial intelligence. So, and deep learning is basically a subset of machine learning only, where the neural networks are multi-layered, and the iteration process of learning is multi-layered. So this is how machine learning workflow basically looks like. We have two models. One is a training and the other one is inference. Where in the training model, we push in a huge volume of historical data or batch data for training the models. And in the inference model, new data streams in, and it gets compared with the historical data, and whatever analytics we have done on top of it, or whatever custom model we have put on top of it, will determine which category the data will be new data will be put on, and it will be added to the historical data for further training. So in both the cases, in training and inference, we see in training that we are using huge amount of historical data, and in the inference we are seeing that new data is coming in as in high velocity and it's streaming in. So in both the cases, we can see that it's a big data problem only. And as I mentioned before, Spark can handle both batch and streaming data. So with Spark, you can also leverage that with the computing. You can write your programs in Python and Scala, apart from Java, and R is also newly introduced into Spark. So next is IoT. So IoT is basically collecting data from connected devices, doing some sort of analytics on top of it, and triggering some action or doing some analytics and making some of your gadgets do some specific kind of jobs. So this is the data flow, how IoT workflow looks like. It's basically distributed into two parts, and one is edge and one is the core. The edge is where the data is getting generated, and you can configure it to be capable of analyzing the data and triggering some action in the edge as well, but that's a different thing. I think it's called fog computing. Next, the data is sent to cloud or a data center where it can be stored and analyzed further for your different use cases. And next, it can be sent to a geo-distributed data lake, or it can be archived somewhere for security, for future use and something. So this slide, we can see that this is the edge node here in kind of blue block, where the data gets generated and analyzed, and some actions can trigger to do certain kind of activity. Then the model data can be sent directly to off-site data store or data center, where it can be further analyzed or secured with some security appliances. So people who are working in these fields, machine learning and AI, will be very much familiar with all these open source frameworks, on top of which TensorFlow, Caffe2, Theno are very famous. But the thing is, these machine learning, these frameworks basically mostly work on HPC clusters, which are very costly, and power consumptions are very high as well. So to address this situation, in itself, these libraries and frameworks are very good in machine learning, but we have these issues like cost issues and power consumption issues. So to address this issue, we have some boutique solutions nowadays, like TensorFlow on Spark or Caffe on Spark. Yeah, so how can we leverage from these boutique applications is Caffe on Spark or TensorFlow on Spark, whatever you're using this distributed computing power of both of Spark and a huge library that is present behind, that is MLlib from Spark, and you can also use the TensorFlow libraries for your machine learning jobs. Whatever functionality that has been in TensorFlow previously is all there in this TensorFlow on Spark, and it can be deployed on CPU or GPU clusters over Ethernet or InfiniBand, whatever your use case may be. So it can be also easily integrated with your present work cycles, data cycles. And the programs can be written in Python, which we all know, Python or Scala, which we all know it's very time efficient. So your development time reduces with these. And if you are using a grid computing kind of thing, then C++ programming in C++ programming languages that can also be integrated with Python and run on this framework.